Assalamualaikum warahmatullahi wabarakatuh. I'm Daffa Alexander and I'm gonna present to you assignment 3 of Astronautics. This is the mission that I'm gonna reconstruct in this assignment. It is the mission of Mars exploration rover B opportunity. It is a trip from Earth to Mars. The rocket carrying opportunity Delta 2 launch at Cape Canaveral SLC 17B, Florida, USA at July 8, 2003, and it's landed at Mars at January 25th, 2004. So that's the overall mission, and you can see here on the left is the picture of the trajectory taken by the spacecraft. So it's going from Mars straight to the moon. So in this assignment, I'm gonna divide it into two parts. So the first part is launch. The second is arrival. In the launch part, we're gonna have the hyperbolic escape trajectory with the heliocentric trajectory also, while on the arrival part, we're gonna have the hyperbolic arrival trajectory only. So the first launch part. So I'm not only include the lift off of the rocket here. I'm gonna also include the heliocentric trajectory part, since it's taken only a small portion of the assignment. So I don't have to divide it into another part. And you can see here the green, the on the trajectory here, the part in green is actually the part that I'm going to be talking next. So at liftoff, the Delta 2 rocket will be burning two things. The first is the 9 GEM46 booster, and the second is XLET. So each of these thing is giving the rocket or the spacecraft an increase of velocity. For the case of GEM booster, the increase of velocity is 2.05, while for the XLET, the increase of velocity is about 3.668. It's calculated using Tsiolkovsky equation provided right here. On the stage 2, the increase of velocity can also be calculated by the same equation as before, and the result is 2.5716 increase in velocity. And from that, we can calculate the maximum attainable velocity, which is 8.2894. Now, that velocity at 8.2894 is the maximum velocity that spacecraft will have if it burns all its fuel until the parking orbit. But we can first calculate the velocity at circular orbit, which is 86538 below the Earth center. It is 7.808 kilometer per second. So compared to the maximum attainable velocity, the velocity at circular parking orbit is actually smaller. So from the calculation, we can conclude that the spacecraft will surely reach the circular parking orbit. Now we come back to the trajectory of the spacecraft. After reaching the circular orbit, the spacecraft will enter the hyperbolic escape trajectory, shown in red right here, while the circular trajectory is shown in purple right here. So first, we should know the elliptic transfer orbit parameter before we're going to calculate the delta V for the hyperbolic escape trajectory by knowing the mu s, res, theta, RMS, And using these two equations, we're going to get the eccentricity of the elliptic transfer orbit parameter and the semi-major axis of the elliptic transfer orbit parameter. And the value is shown here with the eccentricity of 0.2082, while the semi-major axis of 1920.83353 km. Now we're going to calculate we're going to see the hyperbolic escape trajectory. To calculate the v infinity of the hyperbolic escape trajectory, hyperbolic escape orbit, we first gonna have to calculate the velocity at pericenter of transfer orbit, which is VPE given by this phi integral. We should also calculate the velocity of Earth rotating the Sun, or VE, calculated also by phi integral. We're gonna subtract the VPE minus VE to get the v infinity of the hyperbolic escape orbit, which is given here 3.176 after calculating those first two VPE and VE. We're gonna also have the energy needed to escape the sphere of influence of Earth by taking the square of the v infinity, which is given here 10.09 kilometers squared second squared. We now can determine the parameter of hyperbolic escape trajectory, which are its semi-major axis, eccentricity, and the velocity at pericenter. The semi-major axis given by the equation here, the hyperbolic eccentricity given by equation here, and the velocity at pericenter given by the equation right down here. And the value is shown at below that equation, with the semi-major axis is 39510.32, the eccentricity is 1.1654, and the velocity at pericenter is 11.49 km per second. Knowing the velocity at pericenter and the velocity of the circular parking orbit, we can calculate the velocity increase needed for the spacecraft from the circular orbit to enter the hyperbolic escape trajectory given by the delta V1, which is VPS minus VC. This is actually VC. I'm sorry for the mistakes here. So, delta V1 here can be obtained. It is 3.682 km per second. And from this, we can calculate the propellant needed for the propellant mass needed for the spacecraft to enter the hyperbolic escape trajectory. And the derivation of the equation is conducted at the report, while the calculation can be seen here using this equation, and the value obtained is 2,409.73 kilogram. We're going to see later that it's actually not far from the actual data. After that, we're going to enter the heliocentric trajectory from the hyperbolic escape trajectory. Now, we have the Kepler's equation right here on the left, and but we don't have the eccentric anomaly. So first we're gonna have to calculate the eccentric anomaly by using the equation right on the right side here, and we got that the value of eccentric anomaly of E equal to 2.544 radian or 145.764 degree. And from that we can calculate the transfer time at the heliocentric trajectory of T equals to about 210.74 days. You can see the results here at the green box. Now we're gonna enter the second part, the arrival part, which is the part at green here. After the heliocentric trajectory, the the spacecraft will enter the hyperbolic arrival trajectory and then the assumed to be entering the circular parking orbit at the Mars. So the hyperbolic arrival trajectory, we can calculate first the velocity at transfer orbit of the spacecraft entering the Mars and also the velocity of Mars rotating the Sun to calculate the v infinity 2, which is the velocity of the hyperbolic v infinity for the hyperbolic arrival trajectory. So the Vs here obtained is 22.1, about 0.1, and Vm here is calculated 24.424 km per second. We obtain the results of v infinity 2 of the hyperbolic arrival trajectory of 2.33421 km per second. We can also calculate the energy needed to enter the sphere of influence of Mars by taking the square of the v infinity 2, which is 2.334, and we obtain the value of 5.4485 kilometers squared over second squared. We can calculate the parameter of the hyperbolic arrival trajectory here, the semi-major axis, eccentricity, and velocity at pericenter. The semi-major axis using this equation obtained at negative 7,859 km, while the eccentricity is 1.4476 and the velocity at pericenter of 5.4585 km per second. Now, from the velocity at pericenter, we can actually calculate the velocity decrease. It's actually decrease. I'm sorry for the mistakes here. It's the velocity decrease needed for the spacecraft to enter the circular parking orbit at Mars, which first we should calculate using this equation, is 3.489 km per second. We can calculate the velocity decrease by subtracting VPS from VC, and we get that the velocity decrease needed for the spacecraft to enter the Mars is 1.9695 km per second. By the same formula that we use for the part 1 before, we can calculate the propellant mass needed to enter the trajectory of the circular orbit of the Mars, circular parking orbit of the Mars, which the value is given here. It's 600. It's about 602 kilogram. Now we will compare the parameters from the reconstruction data that I have conducted here with the reference data that I get from the internet and from many resources, and we can see that here the error is quite small, relatively small. This error is given in percentage, so it's 0.05% and until 4.3%. So the greatest error is here at the delta V1, which is about 9.2%, but it's still relatively small. Of course, the difference between the reconstructions data and the reference data is there because the simplification that we use that I used on obtaining the reconstruction data, so that I'm only assuming 2-body problem, while it's actually more than 2-body in reality. This is the propellant data comparison from propellant mass at the departure, the reconstruction data says 20409.773, while the reference data is 2010. And that gives about 20% error. So here we can see that from the reconstructions data with the assumption of two-body case, we get higher value of MF. What it says is that for the two-body problem, the spacecraft actually need more fuel to uh, to enter the hyperbolic escape trajectory. While in reality, it's not a two-body problem, and there is a lot of things going on and a lot of things helping the spacecraft to enter the uh, hyperbolic escape trajectory, so that the reference data is actually smaller than the reconstruction data. While here, the MF rifle from the reconstruction data is about 600, while the reference data is 50, only 50. So that gives a really, really big error. And I'm going to say why. That's because we are first assuming that um, the spacecraft, we are assuming the spacecraft will enter the circular parking orbit of the Mars, while in reality, it's not. It's not entering the circular orbit of Mars. It's going to Mars and then dropping the uh, rover and its things. So the in reality the spacecraft is not actually entering the circular parking orbit of Mars, thus giving the MF rifle smaller. So the MF at a rifle is actually should be smaller since it's not entering the circular parking orbit, and that's why also the reconstruction data is bigger. So that's all from me. Thank you for your attention. Assalamualaikum warahmatullahi wabarakatuh.